Now
ম্যাডাম ম্যাডাম এটা যে কাজ করছেন না লাইট প্রেজেন্টটা আপনাদেরই ছিল এটা ইউএসবি কি আপনাদের ছিল না এটা হচ্ছে অন্য কোটে লাগান
ফুটে লাগালাম
কি হবে না নাকি এটা কাজ করবে না নাকি এখান থেকে পর্যন্ত দেখি লেজারটা তো আসছে না লেজারটা আসছে মানে
এইখানে গরম দিতে বেটার লাগে চেয়ারটা সামনে চেয়ারটা
but sitting behind her. Otherwise, I want to see your legs. I want to see your legs. You don't want to. No, or need to. I already saw it. So. How is I'll introduce the picture. Yeah, we're not quite flexible. Thank you. I welcome you all to Ashok Maitra Memorial Lectures 2024-25. As many of you know, Professor Ashok Maitra was our dean from 1975 to 78, and then he was director of from 1984 to 1987. But other than his administrative position, he was mostly known as a great academician and a great teacher. So many of, I mean, I was too young to be a student of his, but there may be some here who were his students. Yeah, there's at least one. And
number of courses.
Highest number of courses. Okay, so 7 courses. So, and those who have been his students, they all remember him very fondly. So in 2012-13, we started this lecture series as ISI Lectures in Probability with Professor Laituri as our inaugural lecturer. But from the next one, 2015, when Professor Jawabarto was the speaker, we changed this name of the lecture series in honor of Professor Ashok Maitra. And since then, we have several eminent speakers, including Remco Hofstad, Matthew Penrose, Palintoff. Last year, it was Maria Eulalia Vares. The idea of this lecture series is to invite one leading researcher globally who is working in probability or related areas so that the students and faculty members in ISI and neighboring institutes can get introduced to the newer areas of research and also build up collaboration with the lecturer. And it has been working quite successfully since 2012-13. Now I'll request our director, Professor Sanghamitra Bandyopadhyay, to introduce the speaker.
Good afternoon. It's a pleasure to introduce Professor Pietro Caputo, who is currently a professor of mathematics at Roma Tre University. He obtained his PhD in 1999. In fact, I also obtained my PhD in the same year in Technical University Berlin under the guidance of Professor Jean-Dominique Deutschel. His areas of expertise are in probability theory and statistical physics, with particular interest in spin systems, interface models, random media, and mixing time for Markov chain Monte Carlo algorithms. He has authored close to 75 papers. He has been on the editorial board of several journals, including Journal of Functional Analysis and Probability Theory and related fields. Annals the Institute Henry Poincaré. I don't know whether I've said it. Okay, so please excuse that. Annals, again, very difficult for me to pronounce, but Annals Mathematiques des Pascal and ALEA, Latin American Probability Journal, ALEA, Latin American Probability Journal. With that, we welcome you to Indian Statistical Institute, Professor Caputo, and look forward to your talk on navigating networks by random walks. Thank you very much.
Yeah.
I hope it's maybe short. Is better? Okay. Thank you very much. Thank you very much for the invitation here. It's a pleasure and honor to be here. So let me thank the organizers for inviting me to this series of lectures, and I'm very happy to be here to meet new students and new colleagues. So please don't hesitate to talk to me after the talk. In the next 2 days, I will be around campus, so chat anytime. And let me start the talk. So as we know, in our everyday life, we experience structures that can be encoded with the mathematical notion of a network. And you can think of the World Wide Web or social networks such as Instagram or airplane routes, biological networks, language networks, and citation networks in scientific papers, say. So by networks here, we think of a graph, and usually we think of a directed graph. So we think of nodes being connected with directed, oriented arrows. Okay, so for instance, in a citation network, paper A has a link to paper B if paper A cites paper B. Okay, same thing with the World Wide Web and Instagram and whatever. So these are huge networks, and there's some huge complexity in the analysis of such networks, and the analysis is key to make scientific developments. So there's a large need of mathematical analysis of such structures that that needs to be developed. And despite some strong development in the last few years, one can say that the mathematical analysis of such structures is still at a very early stage. And as you will see, the models I will talk about are extremely simple, and it is of course desirable to achieve mathematical analysis of much more structured models. But this is what we have so far. If you want to prove some theorem, if you want to do some mathematics. So one of the problems of such networks is that you cannot really analyze them in a global way. But the only access you have is to the local structure. Namely, you start at a node and you are aware of the nodes around you, the nodes that point to you and the nodes that go out from you. But you're not aware of much more than this. And this means that when you analyze a network of this type, the only thing you can do is navigate it by following just the arrows that you encounter in your neighborhood. And this means that an effective tool for this is random walk. Because random walk is a prototype of exploration of your neighborhood by some random process. And this will be the topic of the talk. And by a random walk, what we mean is that if you start at a node, then you look at the possible outgoing edges from your node, and you choose one of them at random. That's random walk. Another popular process is PageRank walk. This is used in search algorithms. If you want to analyze the World Wide Web, say, PageRank walk means that you want to do random walk, but at every step with a certain positive probability p, you move to a chosen neighbor uniformly at random, just like in random walk. And with probability 1 minus p, instead, you move to a uniformly random node of the whole network. So this is like taking a huge non-local jump in the network. This is called PageRank. Of course, there is a parameter p that you can play with, and this we will see something about this. But there are some key questions that we want to understand. And one key question is, does the walk reach a stationary state? So these are finite but huge structures, and so they will have a stationary state, but there is some need of an analysis of the stationary state, and a priori we don't really have access to this quantity. So we want to understand something about stationary state and what it looks like. And the important point about stationary state is that it has been commonly identified as a notion of relevance of a node of the network. So the key idea in PageRank Google algorithms was to identify the stationary state of a node, the value of the stationary state of the node, as equivalent to its relevance in the network. So if you want to give results of some search, then you would put first the node with the highest stationary value, and following the ranking, and you would rank the nodes according to their stationary value. Now, so this makes stationary state, understanding the stationary state, a very relevant point. And another relevant point is, how long does it take to reach this stationary state? This has to do with the speed of convergence to the stationary state and what is called the mixing time. So we will get to that, but let me give you a sketch of what I will talk about more concretely. So from now on, networks will be actually just graphs. You could put weights on the edges and do more general structure, but let's just think of graph. And this will be directed graphs. As I said, these edges will have arrows. So if I have a node from A to B, it doesn't mean that I will also have a node from B to A. This is not necessarily symmetric, so it's directed graph. I will also focus on sparse graphs. And sparse here means really sparse, namely that overall the number of edges will be of the same order of the number of nodes. So this means that in average, every node has a finite number of neighbors. It does not rule out the fact that you will have huge neighborhoods, some hubs. This is not ruled out. It's just about the global number being of the same order. Another feature is that I will look at random models of a graph. Why is this the case? Well, there could be several reasons to do this. Let me just mention two. First reason is that it allows some flexibility in the mathematical analysis. It does allow us to prove some theorem actually about these models. And so this is convenient when we do math. Another perhaps deeper reason is that actually random models allow you to reach some structures that would be very hard to construct by hand. So this is an important feature of random objects, which is at the heart of what is called the probabilistic method, is the fact that there are some things that are desirable, some properties of a network that are desirable, that if you want to construct such a network with such properties, it would be very difficult by hand. One example is if you want, say, an expander graph. This is difficult to construct by hand, but if you do simple random graph models, they will produce with very large probability an expander. So this is an important reason why it's important to study random. So I will actually take a very, very simple model of a network, namely the directed configuration model. Some of you may be familiar with this, but I will review what it's meant by DCM. Then we will study random walk on DCM, and we will try to understand the two questions I mentioned earlier, namely stationary distribution, that is node relevance, and mixing time. Mixing time is how long it takes to reach the stationary state. Okay. And one thing that is very interesting, actually, from many points of view, is to understand the statistics of extremal values of the stationary distribution. Because we said that there may be some nodes which are more relevant than others, and there will be some nodes which are hugely more relevant than others. And you would like to understand what is the statistics of such extremal values. So this will be a point that I want to stress, and this will be a point for which, in this simplified setup on DCM, we will have pretty good answers about this question. This is linked to the so-called power law behavior and power law hypothesis about such extremal values. I will talk about this, so I will mention that, and then I will try to highlight some questions that remain. So as I said, this will be an attempt to communicate some rigorous results, some mathematical theorems about some questions that have been only very recently addressed from a mathematical point of view. So as you will see, there is still a lot of work to be done, and there is certainly a lot of interesting questions to be answered. I put here a number, a few references just to have some pointers in case you're interested in knowing more. Here you can find both the full detailed proofs of the theorems I will mention, but also you can find inside some relevant references in case you want to dig deeper into the literature of such terms. Okay, so stop me if you have any questions, and I'm going to start with with a precise definition of the models and the objects that we are interested in. Maybe there's a way to get this done. It's not. Okay, thank you very much.
Doesn't matter. Hold on. Audio थोड़ा सा
Yeah, you can do it from there.
From there? Yeah. Okay. So, should I go on?
Yeah.
No, it's not going. Back to regular. Okay, so let's start with what we mean by a directed graph. Of course, all of you know this. So I just have a bunch of nodes and a bunch of arrows from one node to another node. This is what we mean by a directed graph. Okay. And a typical thing that you can say about directed graphs is what is the number of outgoing arrows from a node? This is di plus. It's also called the out degree. And what is the number of incoming arrows in a node I? This is di minus, namely the in degree. Okay? So di plus out degree, di minus in degree. And given this, you can construct this matrix Pij, which is just 1 over the outgoing degree, the out degree, for every pair ij that belongs to the edge set. So edge set is oriented pairs. Okay? It's oriented pairs. So 1, 2 belongs to the edge set here, because you have an arrow from 1 to 2, but 1, 4 does not belong to the edge set. So if ij belongs to the edge set, you call Pij 1 over di plus. Otherwise, Pij is 0. This is a stochastic matrix, namely the sum over j for every I is equal to 1, and the elements are non-negative. And this defines a Markov chain, just being the transition probability from I to j, from state I to state j. And this provides the transition matrix for the random walk we are interested in. So random walk on a directed graph, it's simply this stochastic matrix. What does it mean, stationary distribution, for such a random walk? It means a vector pi, namely a vector pi that is invariant under the application of this matrix P. This means that if you start at a node distributed according to pi, you will remain with distribution pi. This can be written in a formula as this eigenvalue equation, eigenvector equation for the matrix P. It's a left eigenvector for the matrix P with eigenvalue 1. Okay? That's the definition of stationarity. And you also require that pi is a probability. So you normalize in such a way that the sum over all pi's is equal to 1. Okay? This defines the stationary distribution just means that if at some moment in your process you are distributed according to some vector pi, you will remain at the next step distributed according to the
So
vector.
can your P be infinite or is finite?
We are working with finite networks. Yeah, good point. Of course, you can do similar things, but you would be a little careful about this object. But this is all I will talk about is finite. Finite, but very large. We will be interested in limits as the number of nodes goes to infinity. So one thing that you can say is that in general, pi is not determined in a global way. but only locally, because this is a local equation. And so you can only understand the network in a local way. There is no way you can come up with a full expression for pi in general. And there are some exceptions. Exceptions are undirected graphs, namely graphs where actually the arrows, when you have an arrow from A to B, you also have an arrow from B to A. So these are undirected graphs. And also more generally, you can have an explicit description of pi in the case of Eulerian graphs. Eulerian graphs means that the out degree is equal to the in degree at every node. And in these cases, undirected and Eulerian, you actually easily see that the stationary distribution is given by the degree itself. Then you normalize it to a probability max. Okay? So what do we mean by directed configuration model, DCM? Directed configuration models is obtained as follows. Suppose you are given a sequence of in degrees and out degrees. You are given these numbers. These are integer non-negative numbers. And they have to satisfy this conservation equation because you want to be able to pair them. So this is necessary. And the configuration model is obtained as follows. Imagine every node equipped with the di plus outgoing arrows and di minus incoming arrows. So just put your nodes in a sequence and draw all the di plus outgoing arrows and di minus incoming arrows for every node. And now you have this number m of outgoing arrows globally, and you can pair them by a bijection with the same number of incoming arrows. And then you can draw an edge, namely an arrow from I to j, every time that an outgoing arrow from I has been matched to an incoming arrow from j. So you look at this bijection as a matching problem from outgoing arrows to incoming arrows. And if there is a matching from an outgoing arrow from I and an incoming arrow from j, you draw an arrow from I to j in your graph. So every bijection gives a graph. These numbers are given. So the degrees are part of the data of the problem. So these are given, and once these are given, you pick a random bijection uniformly at random, and then you obtain a graph. Okay, so this is a random graph. It's a random graph, and here are some examples. In such pairings, you can end up with a loop, just because an arrow coming out of one was matched to an arrow coming into one. Then you get a loop. You can also get a multiple edge. I didn't draw a multiple edge here, but anyway, you could get a multiple edge, namely two arrows going from 1 to 2, if it's allowed. Okay, but this is just one thing that is not difficult to see. It's a combinatorial exercise. Is that if you condition on the event that there are no loops and multiple edges, then you can show that this conditional distribution has uniform distribution among all possible simple digraphs with the given degrees. So here, digraph is just a short word for directed graphs. And simple means that there are no loops and no multiple edges.
So, what's the guarantee that such a thing exists? I mean,
okay, so far this thing exists. Okay, so you may say that G being simple is empty. Okay, yeah, that's a good point. There are combinatorial issues here, but in the setting that I will mention, this will have positive probability, and actually it will have positive probability uniformly in N. Yeah, it's a good point, but whatever it is, if you condition on it, you get a uniform distribution on that. Maybe that could be empty at this stage. Any other question? So far, is this clear? The construction of the model? How we construct the graph we are interested in. Yes. So we make some assumption now, because we said we are given the sequences of degrees, but we want to say what these sequences may look like, and we want to prove results under certain conditions. Let me give you these conditions, and they are quite natural, but there's some caveats that we will discuss in a while. But let's, for the moment, assume that all the out degrees are actually bounded by a constant, say 100, and also that they are at least 2. This is a bit restrictive, but I will comment on this later on. And let's, on the other hand, assume that the in degrees only satisfy a bound, namely that this is a kind of a 2 plus epsilon moment in the in degrees, and you assume that this 2 plus epsilon moment is bounded, again by some fixed constant. Okay, so this means that actually the in degrees could be very large, depending on n. N is the number of total nodes, and you want this n go to infinity. So this in degrees could be actually up to almost square root of n, if this assumption is satisfied. Cannot be bigger than square root of n, but they could be growing with n up to say square root. And this is kind of the interesting point for this talk, because you want to be able to analyze networks which have hubs. And hubs are nodes which have a degree which grows with n. And this is only about the in degree. You don't want hubs in terms of out degree. You could do that, but it simplifies matter for what I will tell you, just to assume it's bound. Yes.
When you said the in degrees can be root n, so
The in degree can be just slightly less than root n, because there's this epsilon. Epsilon is arbitrarily small.
okay,
So
but even if it's so, you mean it's root n for just
some,
I.
yeah.
So then
Hubs will be rare.
even if you assume that epsilon is 0, then summation
It's compatible. I mean, there can be some, the maximum say what could be. Okay, and di minus can also be 0. There's no problem in that. There may be nodes that nobody cares about, and these have 0. So the key point here is that under this assumption, there exists a unique stationary distribution. So the eigenvalue problem I mentioned previously has a unique solution up to normalization. If you insist that it's a probability, there is a unique distribution. And this was developed in papers by Cooper and Fries around 20 years ago. And it was more recently refined. And in any case, under such assumption, it is known that with high probability, why do I say with high probability? Because once you fix the degrees satisfying this assumption, then you have a network that is random. And when you talk about stationary distribution, this is a random object. So you want to say with high probability, namely when n goes to infinity, the probability that this is unique goes to 1. That's what I mean by with high probability here. Also, what this answer Arijit's question, the event that G is simple has uniformly positive probability in n under this assumption. Good. So here are just a few drawings of possible graphs you get. If you have low degrees like 1 and 2, then it's easy. You mostly end up with several connected components. These are strongly connected components. It means that these are sets of nodes such that you can reach from any node to any other node following a path in the thing. And if you have low degrees, you will very likely end up with very many. Here you have 15 nodes and 5 strongly connected components. But if you have larger degrees, like they're all at least 2, then with high probability you will end up with a unique strongly connected components, even if n is small, like 15. Actually, if you take n large, say 500, then with very large probability, you have a unique strongly connected group. And in such situation, you definitely have a unique stationary distribution. Because once you have a unique irreducible component, then this applies unique stationary. Okay, so on such a network, now you want to understand convergence to stationarity. We said that there is a unique pi, which is random. And we say that after t steps, p to the power t is the distribution after t steps when you start at node I. You want to know how far you are from this distribution, from the stationary distribution. And we measure this, it's common in probability to measure this in total variation norm. Total variation norm is just this L1 norm, if you want. Just measuring how far at each node the probability are from the stationary. This also has a natural coupling interpretation, which allows you to do some probabilistic reasoning. But this is the definition here. So let's call DIT the distance from equilibrium time t when you start from node I. T here is a discrete parameter, so that's the number of steps. Okay, is this clear? This definition, yeah.
So, by convergence to stationary, do you mean like a point, like a hub point from where I can go to any node, like some node?
No, I just mean that you start at node I at time 0, and then at time t, namely after t steps, you have some probability distribution of where you will be on the network.
Oh.
And this probability distribution, you want to compare it to the stationary distribution. That's what we are doing.
You necessarily it is a period.
Could be
Necessarily it is a period.
aperiodic. Okay, good point. You can actually prove that with high probability, it is aperiodic, but this will be part of a theorem that will be done. We actually prove much more, but yes, it will end up being aperiodic with large probability under the assumptions that we made. Any other questions? One thing you can always say is that this distance is non-increasing in the parameter t. This is easy. So you make progress towards equilibrium, and we will actually show that it goes to 0, which can be only if it is aperiodic. Okay, so in this case, we are interested in what is called the mixing time, namely, what is the minimum amount of time, amount of steps that you have to make so that the maximum over the initial state of the distance is less than epsilon. This will be T mix epsilon. So you fix a threshold and you want to say how much do I have to wait to get down below that threshold in terms of the distance. And one thing we will prove is that the mixing time is strictly related to what we call entropic time. Entropic time, by definition, is just log n over h, where h is this quantity here. This quantity can be interpreted as a Shannon entropy when you take a jump from node I. What is the entropy of that jump? The entropy of that jump will be just the log of di plus, because there's di plus possibilities, they're all equally likely. But you want to sample the node I according to the in-degree distribution, for reasons that I will try to explain. And so this is a kind of an average Shannon entropy for your work at each step. And you want to know, this T-ant is essentially telling you how many steps of size h you have to make to reach log n. Log n is some sort of the maximum entropy possible in a set of n nodes. So that's the interpretation of entropic time. And what we will show is that the mixing time of the network, under the assumptions I gave you, is actually given by the entropic time. No matter what the epsilon, This is kind of strong statement. As soon as you fix epsilon between 0 and 1, strictly between 0 and 1, then essentially what you have to wait is entropic time. Okay? And this can be interpreted as a cutoff phenomenon. Let me explain why this can be interpreted as a cutoff phenomenon. The cutoff phenomenon lies in the fact that this depends very weakly on epsilon. So whether you want to be 0.1 close to equilibrium or 0.9 close to equilibrium, essentially you have to wait the same amount of time. So that means that up to some time that will be sort of entropic time, you will be as far as possible from equilibrium, and after that time, you will be as close as possible to equilibrium, namely at equilibrium. So one way to picture this is to look at the function di at time t, where t is given by some parameter rho times entropic time. Essentially, what you're doing is you're putting yourself on the scale of entropic time, and you are multiplying this by a parameter rho, and seeing if rho is less than 1 or rho is bigger than 1. And if you plot this function, what you can prove is that as soon as rho is bigger than 1, when n goes to infinity, this becomes 0. And as soon as rho is less than 1, when n goes to infinity, that becomes 1. The maximum possible value for the distance is 1. So you are as far as possible from equilibrium up to here, and then you are as close as possible to equilibrium from here on. This is called the cutoff phenomenon, and it's something that you may be familiar with since it has been very deeply studied since the 80s in these pioneering papers by Aldos and Diaconis, where they showed that if you're shuffling cards, essentially there is for a certain number of shuffles, you are essentially as far as possible from being mixed. And there is a moment where very rapidly, with 1 or 2 shuffles, you essentially collapse to being fully mixed. This is cutoff phenomenon in the case of card shuffling, and this is cutoff phenomenon that we detect in the case of random walks on random networks, as under the assumptions that I discussed. And there were previous works dealing with this problem in the case of undirected networks. These are interesting, very important work by Lubetsky and Sly, Benamou Salez, and then further work by very sticky Lubetsky, Veres, and Sly. And these all show that there is cutoff. And cutoff here occurs with high probability. Let's remember always that all this depends on the realization of the random graphs that's underlying our problem. So things are meaningful when they happen with high probability with respect to this realization. And as you may know, cutoff phenomenon is not something satisfied by all Markov chains. There are also Markov chains which make progress towards equilibrium gradually. Cutoff phenomenon is only for those Markov chain which have an abrupt transition from extremely far from equilibrium to extremely close to equilibrium in a very, very short time. Let's look at some pictures of simulations and see what we can say more concretely about such thing. So this is an illustration of the theorems I'm talking about. So suppose you are sampling a network, a DCM with 15,000 nodes, and you divide them into 3 sets of 5,000 nodes each. And the first set has outgoing degree and incoming degree given by 3 and 2. The second set has D plus 3 and D minus equal to 4. And the third set has 4 and 4. Is it clear, the model here? And then you sample according to this uniformly random bidirection, as we said, the DCM. Okay, very good. Now you run your random walks and say you start at node 1. So you start at node 1, and you run your random walks. And then you plot the distance from stationary, namely this d1t. You plot from time t equals 0 to time t equal 20. Okay, so this is after 20 steps. And what you see, this is just a plot from the simulation. What you see is exactly a cutoff type profile. Namely, the distance is essentially 1 for a while, then it drops in only very few steps to essentially 0. So this means there is a moment in your walk where you essentially collapse to stationary. And then this is even more interesting. Let's look at the histogram of values of n times the invariant distribution. What does it mean here? So the invariant distribution pi, we said it exists, it's unique, but we don't know really its value. That's what we are interested in, actually. And so you may want to plot from the simulation what the values are. One way to plot the values is to do an histogram. So to say how many nodes have a certain value of the invariant distribution. And it's convenient to normalize by multiplying by n because the invariant distribution has to sum to 1. So its typical order would be 1 over n. So if you multiply it by n, you get something of order 1. And now you can say, suppose here I'm interested in how many nodes have value exactly 1. And n pi is exactly 1. Then this is this column here, and this will give you the height of this column will give you how many nodes have value exactly 1. Of course, it doesn't make sense to speak of exactly 1. It will be maybe 1 minus epsilon, 1 plus epsilon, so you can do some discretized column. Yes?
How is pi I and di related?
Exactly. That's going to be the main question. D is given in this example in this way. This is the example I'm talking about, and this is the simulation for this example. So you can see that there is a bimodal structure here. And the bimodal structure means that there's a bunch of nodes which will have their stationary values around this 0.6, 0.7 something. And there's a slightly bigger bunch of nodes that will have their values around this here, 1.2, 1.3. Okay? This is kind of interesting. It should be related, at least intuitively, with the fact that the in-degrees of this node are either 2 or 4. And it's natural to think that a node which has a high in-degree will also have a high stationary value. Makes sense? It is also intuitive that a node with a small in-degree will have a small stationary value. And this should sort of intuitively justify this bimodal structure. There will be more nodes with a high stationary value according to this 4 and 4 in-degrees, and only a bit less with this value according to the 2. It's intuitive that a node with a high in-degree should have higher relevance, because if you think of a citation network, a paper with a lot of citation should be a relevant paper, right? That's one way to put it. It's not necessarily going to be the most relevant paper, but paper with the highest number of citation is close to being a relevant paper, right? This is the way to put this question into quantitative analysis. Okay, please interrupt me if there's some question. I'm happy to answer. This is kind of an important picture to grasp, to have a feeling of what is going on with this random walk. So this should be understood as the distribution of the stationary values.
How will the graphs change? Swap in.
If we swap in degrees and out degrees, that's a good point. certainly the invariant distribution will change. But you could use the same bijection, but you get a different graph and with a different invariant distribution, which could be difficult to relate one from the other. Let's keep in mind that if you take a graph that is Eulerian, say that has say 3, only, suppose you took a graph with 15,000 nodes and they all have 3. Okay, this is the Eulerian graph. Then what will happen here is that you will get a single line, because there's only one value of the stationary distribution, which will be 1 over n. They all have the same probability, and this will be a single line. So it's like a delta function. The distribution will be a delta function. Instead, as soon as you are non-Eulerian, you can actually prove, and I will tell you something about this, that you will get an absolutely continuous distribution. So it's quite powerful, the type of things you can say about this invariant distribution. As soon as you don't have a combination of delta function, you will get an absolutely continuous. Okay, I will tell you more about the theorem we have.
For Eulerian graph, it is called the doubly stochastic. That's why it's 1 y and 1 y. That's why.
Yeah.
Doubly stochastic PI.
Absolutely, yes. And then the invariant measure is simple. Is
Yeah.
Yeah, absolutely. Okay. So, okay, then let me formulate what I told you about the cutoff phenomenon. You can formulate it in this theorem. One way to be formal about this cutoff phenomenon is formulate this theorem. As soon as rho is different from 1, say is less than 1 or is bigger than 1, then the distance from stationarity at time rho times this entropic time is given either by 1 or 0, according to rho being less than 1 or rho being bigger than 1. And this will occur uniformly in the initial state. So it's quite a strong statement. And this quantity will go to 0 in probability, because as we said, these quantities are random and they have a distribution that is governed by the random graph. And you want to say that with high probability, these events occur. And one way to put it is by convergence of probability. But if you're not familiar with this formal notation, don't worry. The result is just this cutoff that I mentioned earlier. And another way to put it is that the mixing time is actually equal to the entropic time up to smaller order corrections as n goes to infinity.
Do you know the exact order?
The correction?
Yeah.
Yeah, that's a good question. Actually, we do. If you make a bit more of assumption on the degrees, you can control actually the window of this cutoff phenomenon, and exactly you can say that if this is a log n, if this is a log n time, that because this entropic time is of order log n, then the window will be of order root of log n, and you can actually plot the explicit profile at that scale. So it's a precise mixing result. I will not tell you about proof of this, but if you want, I am happy to discuss this later. The proof involves several steps and several. So it'd be better to postpone that. Let's come to the discussion of the stationary distribution. We want to understand the picture we had here, this part, because this theorem I gave you is about this part here. But now we want to say something more about this part. What can we say? The question of Arijit was, what is the relation to the in degrees and or the out degrees? Okay. So formal way to write the distribution is to take the empirical stationary distribution. Namely, you take n times pi and you look at the empirical values associated to this data. Okay, this is, you call this vector psi. This is telling you exactly the height of the histogram we plotted in that picture. And the theorem we have is that if you look at one Wasserstein metric, if you don't know what this is, doesn't matter. Just think of some way of measuring a distance between this probability. This can be seen as a probability measure and another probability measure L. And you say you can prove that there is actually a limiting probability measure L such that this converges to zero in probability, namely your empirical distribution is well approximated as n goes to infinity by some limiting distribution L, which is not very explicit, but it can be written as the unique solution to an explicit distributional fixed point equation. So it must satisfy some fixed point equation. Okay. And so in principle, you can derive certain properties of your limiting measure L from this fixed point equation. In the example we had plotted before, this this quantity here will be very close to the limiting law. So this can be understood as the density of the probability distribution L that I mentioned in that theorem. So this will be the solution of some fixed point equation as a distribution. That's the result here. And again, I will not really have time to talk about the proof of this, but something that is important is that both results about the mixing and about the stationary distribution crucially use the fact that we have a sparse model, and the way we constructed our graph implies that locally we have a tree structure. Because locally, when you explore the neighborhood of this random graph, with large probability around a fixed point, around a given point, you will see a tree for some time. So if you fix, say, the depth of your neighborhood to be a fixed number, up to that fixed depth, you will see a tree. Cycles are rare in these models because they are very sparse. So before you see a cycle, you have to go a little far. That's going to be crucial to prove all of these results. And the fixed point distributional equation comes from the fact that on the tree, you can actually derive a recursive equation for your distribution. So if you are able to exploit this local tree-like structure to compute limiting distribution, then you can compute the limiting distribution on the tree. And on the tree, you can write recursive equations, and this is, you need to do this carefully. You need some martingale convergence and some careful argument. That's the main idea here. And why are these fixed point equation interesting? Well, first of all, they have been studied quite well. This type of fixed point distribution of fixed point equation have been studied quite well in conjunction with the branching processes and Mandelbrot cascades, and these are kind of well studied objects, and you can from works that were done on this topic, you can derive existence uniqueness, tail behavior of solution, and various things. For instance, what I told you about being absolutely continuous can be derived from these results. So the difficult part here is to prove that actually the finite n object can be approximated by such a limit. Okay, very good. So one thing that we want to understand is the extremal values, because what I told you about the convergence of the stationary distribution has to do with the bulk behavior, namely the typical values. Empirical distribution will give you the typical behavior of the stationary line. Instead, we could be interested in understanding the maximum value of the stationary distribution, for instance. This is the most relevant node. If you understand this guy, you would know who is the most relevant node. And also you may be interested in understanding a ranking, who is the most relevant, the next most relevant, and so on and so on. Another thing you would be interested in is the minimum value. The minimum value is not so interesting in terms of relevance, but it's interesting for other reasons because it will tell you what are the essentially difficult nodes to reach. And these play an important role if you are interested in the so-called cover time of the network, namely, how long does your random walk take to visit all of the nodes? If you're interested in cover time, there is a nice theory by Cooper and Fries, who developed quite a powerful technology that essentially will allow you to understand the cover time once you understand the minimum values of the stationary distance. Because these are the nodes that will play the main role in giving you the time you need to cover the whole network. Because these are the most difficult ones to reach. For the purpose of today's talk, just focus on PyMax. And later on, I will tell you more about the ranking of the. So for PyMax, as we said, the question of understanding PyMax is related to the question of understanding the maximum in degree, right? But maximum in degree is something trivial because I know the sequence of in degrees. This is given, so you may cook up the sequence the way you want, and you will know what the maximum is. And then you may try and see, is this maximum really also the most relevant node? Is this really also giving you the maximum of the pi? And usually you find that it's not, because there will be some node that has higher value than the one which has the highest in degree. Okay, so usually the most cited paper is not the most relevant. The analogy we discussed there. One theorem you can prove is something of the following form. If all nodes have bounded degree, so if everything is bounded, so there's no hubs. Something that is interesting is that you could think that all of the stationary values are all essentially the same. But actually, there is logarithmic fluctuation. And the logarithmic fluctuation can be quantified in this term. Namely, the pi max times n is not 1, but it's growing logarithmically with n, where the constant the power you have to put to the log is something explicit in terms of the statistics of the node. This is something you can prove about fluctuation with respect to the mean of the pi, because the mean of the pi is of course 1, n times pi squared must have mean 1, but here the max will have logarithmic fluctuation. Okay, but this is really
This is the same on index is same on both upper bound and lower bound. It's only the constant.
it's only the constant that changes.
The log
The log is the same. So you really capture the size of fluctuations here.
Sorry.
But this is kind of a simplified setup because you don't have hubs. You're more interested in cases where you have hubs. So let's take a case where you have hubs. And one way to construct hubs is by taking an in degree sequence with a heavy tail. So you just assign, say, IID random variables for the in degrees, and some of them will be very large if you use a heavy tail. So let's take this example. Let's take the heavy tail being a power law distributed with index kappa equal 2.5. This is kind of an arbitrary choice, but let's say we take 2.5. So this is a fairly heavy tail. It's not the heaviest you can think of, but and let's take all out degrees being equal to 2. It doesn't matter. The out degrees do not play an important role in terms of stationariness. So let's take them, all of them equal to 2, and instead the in degrees will be drawn from a random IID sample of a power law with index kappa 2.5. Okay, so let's just look at the blue and the yellow. Forget about the green and the red. This is a different story. But let's just look at the blue and the yellow. It turns out that if you do a simulation, these are the number of nodes. So these are showing that there is some stability in the statement, because it doesn't really depend on the number of nodes here. It turns out that the ratio between the pi max and delta minus over m is essentially a bit larger than 1, something like 1.3 something. Whereas the ratio of the pi of the node with the highest in degree, this is pi delta minus, with delta minus over m, is essentially 1. So let me explain these numbers. Delta minus over m is the reference value you would look for when you think of the stationary value of the node with the highest in degree. Delta minus is the highest in degree, and then essentially you would expect delta minus over m roughly for that stationary value. And in fact, if you look at the stationary value at the node with the highest in degree, you get asymptotically 1 for this ratio. It's a good guess what we had. On the other hand, if you look at the stationary value of the maximum, if you look at the maximum stationary value, this ratio will be higher, but consistently higher, uniformly in n, in something. So it's 1.3 something. For this example, of course, these numbers will depend on the tail of the heavy tail. Okay, so that should give you a hint of what to expect in terms of ratio. And you can also plot the distribution actually of this pi max versus the distribution of the pi delta minus. This will tell you that if you do many iterations, say with a fixed number of n very large, you can get certain distribution for the pi max and a certain distribution for the pi delta minus. And they will be, of course, slightly separated because one has to be bigger than the other. Okay, so this is what you have from simulation. But now, what can you prove? So ideally, what you would like to prove is that if you sample the in degrees with a power law, then this is the so-called power law hypothesis. Then your stationary distribution will also have a extremal value statistics which has the same power law of the in degree. This is a conjecture that has been around for some time in these models, and it's called the power law distribution. Maybe I will just jump to that because that's the most interesting thing here. So to define that properly, let's look at the number of nodes which have in degree larger than some x, and normalize this by 1 over n. So this is the tail, in a sense, is the tail of the in degree, empirical tail of the in degree. So this is something you know. You have access to this because you have given the in degree. And this is something you don't know, namely the empirical tail of the stationary distribution. But you would like to understand whether this object is related to this object, namely, if you take x very large, this will give you the ranking of the highest in degrees, and this will give you the ranking of the highest stationary value. So to make things work, we will make an assumption that the in degrees have some power law behavior. And a way to formulate this is to take some index kappa that I will assume larger than 2. Forget this epsilon. This is just for to make theorems work, but But essentially, you can take epsilon arbitrary and small, so think of epsilon being 0 essentially. Now you assume that there are no nodes that are bigger than n to power 1 over kappa. This is natural if you have a power law with index. And then you assume that the number of that the empirical tail of your nodes follows this statistics. Namely, if I take x to be n to some power, which is the power between 0 and 1 over kappa, then this is really going to be given by n minus kappa to that power. This is very natural if you have a power law of index kappa. So in particular, if you sample your in degrees with a Pareto law of index kappa, this is exactly what you will see. So one way to cook up this situation is by just sampling your in degrees with a Pareto law of index kappa. So if you want, just take this definition for the in degree. IID with this Pareto law. Then you will satisfy this. Okay? Also, the caveat I was mentioning is that I need to take kappa bigger than 2 because we had this 2 plus epsilon assumption at the beginning, which is a bit restrictive. You would like ideally a 1 plus epsilon assumption. 2 plus epsilon is a bit restrictive, but that's what we can do. I can tell you more about this if you want, but it's a bit technical. Anyway, that's what we assume. We assume that there is a kappa larger than 2 such that these statistics are satisfied. And one concrete way of satisfying all this is by taking from the start your in degrees with a Pareto law of index kappa. Now, under this assumption, we would like to prove that this guy, namely the unknown guy, has the same statistic. So we have seen from simulation that the highest stationary value will not be necessarily the highest in degree, but we would like to say that the statistics of extremal value is the same. And that's what we prove. So this establishes the so-called power law hypothesis, because it says that as soon as this assumption is satisfied with some kappa, then the same thing is satisfied by the empirical tail of the stationary values with the same kappa. So if you look at nodes in your network, which have stationary value larger than n to power a, or any a between 0 and 1 over kappa, you will see as many as in a power law distributed sample. Okay. Does this make sense? So this is a quantitative way of saying that as soon as you have some power law tail for the in degrees, you have some power law tail with the same index for the stationary. And what else? One interesting thing is that these results will go through if you add a PageRank structure. Namely, what is PageRank? We said that at every step, PageRank decides whether to follow a random walk or to jump to a uniformly distributed size. So let's say the probability alpha is the probability to jump to a uniformly distributed side, and probability 1 minus alpha is to follow the random walk. So this gives you this new transition matrix, and you can actually even take lambda to be some other distribution. It doesn't have to be uniform. This is sometimes called the customized PageRank. If you want to use a personal distribution of the website that you care about. Okay, so it's not difficult to see that as soon as alpha is between 0 and 1, you have a unique stationary distribution. This is just because if you have positive probability of jumping to with lambda, then eventually you will jump there, and this gives you a unique probability. This gives you a unique stationary distribution. And one thing you can do is, again, analysis of mixing time and cutoff phenomenon for such a problem. this has been worked out, and we did this 3 years ago with a PhD student in Rome. And here you can look at, again, the power law hypothesis, namely, can you say that if your in-degree nodes are power law distributed, can you say that also the PageRank by alpha lambda, namely the new stationary distribution, is also heavy-tailed with the same index, this power law with the same index. And what you can prove is exactly this result, namely that if you fix kappa greater than 2 and assume that your in-degrees are given with this power law with index kappa, then you can prove this theorem, namely that as soon as lambda is sufficiently well spread out, say it's uniform up to little o of 1 correction in the exponent, then you can prove exactly the statement that we had before, namely that you have the same power law behavior for the extremal value of the new stationary distribution, which is so-called PageRank score. It will have exactly the same power law behavior. This was something that was kind of a question that has attracted a lot of attention, also for practical reasons, because the World Wide Web has empirically a power law distributed structure of in-degree. And then you ask, what is the statistics of the PageRank score? And what is interesting is that this result does not depend on the value of alpha you choose. The PageRank score is well known to be strongly dependent on the parameter alpha that you choose. That's one thing that has been observed. That the PageRank score does depend on the parameter alpha. It's not independent. So on the other hand, the power law behavior is not depending on the power alpha, at least for this simple directed configuration model that we're looking at. And so this is kind of an interesting, strong result for this model. It had been addressed in a different flavor in a couple of papers where they actually looked at the kind of an average result. But this is more quantitative in the sense that you're really looking at how many nodes in your network have that statistic. And the previous results had to do only with the tail of the bulk, which intuitively could be connected, but it doesn't have to be necessarily sufficient to get this information. Okay, so that answers the question for the PageRank score. Let me end up with yeah, 1 minute.
Yeah.
I just end up with a couple of
that would be
open questions, and then if you have any questions, I'm happy to. So on the technical side, one thing that is not satisfactory about this model is that we assume 2 plus epsilon moment. And as I said, it would be nice to assume only 1 plus epsilon. At least one you have to assume because you want the total mass to be conserved. And otherwise, if you don't have at least one moment, then this doesn't happen. It will not happen. On the other hand, it is interesting to go to 1 plus epsilon because actually real networks like the World Wide Web are estimated to have an index kappa that is between 1 and 2. So it will be between 1, it will have a 1 plus epsilon moment, but it will not have a 2 plus epsilon. So that is a good motivation to go down here. But this is something technical that needs to be worked out. On the less technical side, well, okay, relaxing the assumption on DI plus is a bit less urgent for me, but that could be also something to look at because we do assume that they are bounded, so it's a bit restricted. But I think this is a bit less important. What is really, I think, more important is to go beyond these simple models of directed configuration model and go into models which have a richer structure of correlation and which have so-called clustering, namely the possibility of cycles at a small distance. So neighborhoods, many neighborhoods with cycles that is definitely much more similar to real world networks. Because this tree-like structure, local tree-like structure that we have here is not very typical in actual. So there's some partial results about dynamically evolving networks. This is also kind of an interesting direction, namely when your underlying graph is not fixed once for all, but it has itself some dynamics, some Markov chain dynamic. This only a very preliminary result addresses this question, but this is something I think that should be looked at. But let me stop here and get a question on that.
Questions, if anyone?
In the power law, how do you choose the out degree?
The out degrees in those for the simulations were just equal to constant.
But like it will depend on the in degree, right? In degrees are random.
Yes, but okay, you want to know technically how you perform the simulation, or because
you choosing the in degree.
you can always sample your in degrees at random, and then with the given sum, you can just redistribute the out degrees. That's a practical way to do it.
And the result does not depend on the out degree.
No, the result does not depend on the out degrees. It holds, these results hold as soon as your out degrees are bounded between 2 and some constant. Under these assumptions and under, say, the power law assumption for the in degree, you know.
Another question is, in one of the examples, you had this plot where you had two nodes.
Yeah.
Two nodes. So can you explain that with this using like limiting this?
Yes, in that case, you can solve not explicitly, because it's not going to be an explicit probability density, but you can actually detect the bimodality from the fixed point equation.
I'm more familiar with the undirected side of things. So are there like analogs of figures inequality here and relaxation time related to mixing time, etc.?
Yes, okay, you can definitely do some Shiger inequality. Namely, here you could try to get spectral radius bounds on the eigenvalues of the stochastic matrix. This has been done in some under some assumption, bounded degrees and things like that. It has been looked at, but that this is a non-reversible setting, so that will not provide immediately information on the mixing time. You would have to do something more, and the type of information we get here is much finer than the information you could get just by comparing the relaxation time and so on. So yeah. We bypass that type of approach, go directly to mixing time.
You have any closed form expression for the stationary distribution, given any degree sequence? You provide any algorithm?
The only closed form expression is this fixed point equation that has to be satisfied by the limiting distribution of the stationary values. So there is no closed form. And you shouldn't expect to have one, because it's like solving an eigenvalue equation, and there should be no explicit expression for that. But an eigenvector.
What is it? You just mentioned that it's not necessarily that the one with the highest degree has the highest value. That's fine. So the question is it likely that the one with the highest pi I has several nodes going which are linking to it, which have high degrees? Because if you define geometry of the graph in a reasonable way, then that this can be made precise.
Yes, that's actually something we use to provide lower bounds on the maximum value. Namely, one way to see how large has to be the maximum value is to construct a neighborhood, in neighborhood, namely, follow all the nodes that enter at some point in that node. And that, if you put enough I in degrees in that neighborhood, then you will construct sort of the highest possible pi. Of course, you cannot put too many, because this will have a small probability. But you want something that happens somewhere with large probability. So compromising between these facts will give you the right scale at which you see the highest value. So this, yeah, there is some analysis of the in neighborhood of these guys, and these guys would be characterized by having as many as possible large in degrees, not only themselves, but also in their in neighbors.
Hey, we have one last question.
You were talking about if instead of considering just the max, we consider the first constant number of entries, does that follow a point process or does it have a, in the n-pi distribution? So if I rank the first 100 or something, does that follow a point process or is there?
Yes. Giving the exact point process distribution may be difficult because we have these epsilons around here that are difficult to remove. But morally, that's exactly what is going on. So morally, just like in standard heavy tail phenomena, you have a Poisson process of the rank of the maximum value. But to prove that literally, I think that's very, very difficult here. This is kind of a weaker form of exactly what you. I don't think it's easy to go beyond this weaker.
Okay, it's good to see that there are so many questions, but Professor Caputo will be in room 3.6 tomorrow and also on Friday. Tomorrow there will be also a lecture on random permutation dynamics, again from 4:30. So let's thank him once more.
Thank you.
And you see you tomorrow. Is there anything